Okay, sorry, it's late in the afternoon and there wasn't a flow. Just don't even ask. Okay, so if x is 0 and y is 1, you get 3 plus z equals 0, so z is negative 3. So the point 0, 1, negative 3 is one of our vectors. And if x is 3 and y is negative 2, yeah, that works. If x is 3 and y is negative, somehow arithmetic just getting jumbled up here. But if x is 3 and y is negative 2, we get 6 and negative 6 plus z equals 0. Well, that'd be 0 plus z equals 0, so z would be 0. So 3, negative 2, 0 is a point. Now, the way I actually arrived at some of these points is maybe a little bit interesting. So still, we'll just hold on to the idea that our vectors v1, v2, and v3 would be these three sets of these three ordered triples. Okay? Then I say, okay, well, we can confine our attention to the xy plane. If we're in the xy plane, that means that z is 0. So, okay, down here in the plane defined by the x and y axes, that plane is horizontal through the origin, z is 0 everywhere on that plane. In that plane, y equals negative 2/3 x, because if z is 0, we have 2x plus 3y equals 0. If we solve that for y, we get y equals negative 2/3 x. Well, y equals negative 2/3 x forms a line that I've depicted here. Now, my shading indicates that we go parallel to the z-axis from the y-axis, parallel to the x-axis to get to this line. So this line is in the xy plane. And I can make that even less clear, but hopefully more clear, by doing this kind of shading. Okay? Then, if x is 0, then what do we have? We have 3y plus z equals 0, so z equals negative 3y. So in the yz plane, we have a line here with slope negative 3 through the origin. This is a line with slope negative 2/3 in x and y through the origin. And I actually just then said, okay, on this line, if y equals 1, then by the slope z has to equal negative 3. On this line, if x is 3, which I chose because it multiplies with 3 in the denominator, y is negative 2, so there's a point. So that's how I got these points, but I also talked a little bit about these lines. The task on this problem now is to ask the question, can we get a non-trivial linear combination of v1, v2, v3 that's equal to 0? Now, we know that that's the test for linear independence, don't we? Okay, we talked about that previously, and it's, of course, one of the topics that we're moving through this week. So, is C1v1 plus C2v3 plus C3v3, did I say that right? C2v2, C3v3, equal to the 0 vector. Is there a non-trivial solution where C1 equals C2 equals C1, C2, and C3 are not all 0? Well, this equation, as we know and have known for some time, can be written as a matrix equation. And here's the matrix equation, okay? 1, 1, negative, I didn't write the matrix equation correctly. I was careless when I wrote the matrix equation. These rows should have been columns. So I'm not going to change that right now, but I'll change that in a minute. So I'm just going to say, okay, these rows should have been columns, so I should have done actually the transpose of this matrix. Okay? Still, the idea remains, because I didn't really do anything with the matrix. Okay, if I take the transpose of this matrix and invert it, then my solution is C1, C2, C3 equals the inverse matrix times the zero vector. But of course, the inverse matrix times the zero vector, any matrix times the zero vector, gives you the zero vector, right? And that would mean that C1, C2, and C3 all have to be zero. Well, that will be the case if the matrix is invertible. So if the matrix is invertible, there is no way to get a non-trivial set of numbers C1, C2, and C3 that make this sum zero. Okay? Can't be done. The vectors would be then linearly independent. The only way the sum could be zero is if all the constants are zero. If this matrix is invertible. Well, turns out this matrix isn't invertible, and we can easily verify that. Okay? The determinant of this matrix is zero. We can calculate it. 1 times this is 1 times 6, and 3 times this matrix is 3 times -3 plus 5, okay? And that's 6. And something's wrong. Yeah, the determinant of this minor is -6, so the determinant of 1 times this minor is -6. The determinant of 3 times this minor is 6. They add up to 0. So the determinant is 0, and it had to be true if these vectors are all on the same plane, and we'll see why that is. So the determinant is 0, so the matrix is not invertible, so we don't have this. So that means that we're going to be able to find C1, C2, and C3. Not all 0, but make the sum 0. And we can solve then this matrix equation by reducing the auxiliary matrix, or the augmented matrix. Auxiliary doesn't have a G in it, does it? Sorry, it's getting late. Okay. So, here's where we are. We've got 3 vectors, three points in this plane. We know they form a vector space by the condition we've proven here. And here are our 3 points regarded as 3 vectors. Sum of these is 0, provided the transpose of this matrix times C1, C2, C3 vector is equal to the 0 vector. If the matrix is invertible, then all the C's are 0, but the matrix isn't invertible because its determinant is 0. So we can solve this matrix equation by reducing an augmented matrix. That means we can find C1, C2, C3, not all 0, such that this linear combination is 0, so that this set of vectors is not linearly independent. Now that's a big deal. And as a side note, that means that any of the vectors could be expressed as a non-trivial sum of the others. Okay? Which means that we only need 2 of these vectors to form a linearly independent set and to span the plane. And we'll talk about that in our next class. Actually, we're going to talk about that in a video that I'm about to do because you're going to need to watch that video.